Welcome to your next lesson. This is 11.2. We're going to get started into covering these important parts now, specifically starting with probability. So I want you to start by thinking to yourself, what's the probability of a coin landing on head? Or what's the probability of rolling 6 on a normal die here? Right, so let's think about this. And I hope you guys have some background with this, remember this a little bit. What's the probability of a coin landing on heads? Well, you can land on heads or tail. So your chance is a 50% chance. What about for a six-sided die? Well, you have the options of 1, 2, 3, 4, 5, or 6. 6 is only one of those options. So this is going to be 1 in 6 times it's going to go onto that, or that's going to be about a 16.7% chance. If this is a little confusing, that's okay. We're going to cover how we get to these in this lesson. But before we jump in, I want to clear up a couple of things that can be confusing. Let's talk about the difference between probability and odds. Probability is the likelihood of something happening. So in the example of flipping a coin, your probability of something happening, right, is 50%. You have a 1 chance of getting it for every 2 possibilities, right, of something happening. Whereas odds are the chances of you getting it versus the chances of you not. So the odds of this landing on heads, there's 1 chance of you winning in comparison to 1 option where you lose. So this is an odd. This is what we're not going to be dealing with. We want to be looking at the chance of something happening over the total possibilities, not the process or the probability of it occurring against the probability of it not occurring. One more thing about probability, you'll notice they're in percentages here or in fractions. Probabilities range between 0 and 1. Your probabilities range between 0 and 1, where 0 means there's a 0% chance of it happening, 1 being a 100% chance. Right? If we're at 0.5, that would be a 50% chance. So you'll see probabilities more frequently expressed as a decimal than as a percentage. All right, now we're going to be dealing with 3 different types of probabilities. We have, let's write this out. We're going to have experimental probability. We're going to have theoretical. And we're going to have something called geometric probability. All right, so experimental probability is the probability is going to be the number of times something happened and that's going to be divided by the total number of trials, or the total number of times you looked. So the experimental is the number of times it happened over the total number of trials. Theoretical is going to be the number of possible outcomes where you win. Number of winning, we'll call this winning outcomes. And that's going to be divided by the total number of outcomes. And then geometric is going to be the winning area, so the area where you have a chance of winning. And that's going to be divided by the total area. Right, so let's look at an example of each of these because they can get a little confusing, especially the difference between theoretical and experimental. So experimental, let's talk about flipping a coin. Let's say you flip it 5 different times, you get that it's heads, then tails, then tails, then tails, then heads. So the experimental probability of getting a heads would be, how many times did it happen? It happened twice. How many trials did we have? We had 5. So it would be that or 40%, 0.4. Whereas we know theoretically, or we know that generally, we expect this to be that when our probability of heads will be, well, there's one chance of getting heads and there's 2 total chances, or it's 50%. So these two numbers can be different, what we expect and what actually shows up. This is why we try so hard to get the theoretical number when we're talking about probabilities or statistics generally. And then geometry is something like, let's say you have a rectangle that is side 10 and 5, and you're trying to win by getting inside a 2 by 2 box. So that would be, scroll down. All right, so that would be, our area of winning would be a 2 by 2 or a 4-inch or unit area divided by 50, or that would be 2 over 25, which would be an 8% chance of getting that. All right, so those are our 3 different types. We're looking at experimental, where we're looking at the total number of times it happened over our trials, the theoretical, where we're looking at winning outcomes over our total outcomes, or our geometric, which is our area. One thing to note here, a couple of definitions. First of all, the total number of outcomes, we have a special name for that in statistics. Or all of the different possible outcomes. We call that our sample space. So this is called a sample space. And this is a word that you'll hear me using, so this is just one to become familiar with. Actually, we don't need a box. Let's just underline that. So that is a sample space. And the other thing, notice how we have this discrepancy. We have a difference here between this 40% theoretical chance and this 50% chance. We have something in statistics called the law of large numbers. And what the law of large numbers says is as you get a larger and larger number of trials, you're going to get your experimental probability getting closer to your theoretical. So as you get a larger number of trials, the experimental will get closer to the theoretical. And you may have already had some intuition for the law of large numbers, right? If you flip a coin twice, or if you flip a coin once, and it lands on heads, you have a 100% chance of getting that. But as you flip it 50 times, or 60 times, or 100 times, or 1,000 times, it'll start to get closer to 50%. That's really what this is saying, is the more you do that, the closer it will get. And there's ways you can even do this on your calculator or online, where you can sort of see how that number approaches the theoretical number. All right, so let's start dealing with some examples. Let's say that you were looking at a group of people and you saw that 6 of 20 people were wearing red shirts. And if you're asking what's the probability that somebody is wearing red, somebody picked at random was wearing red, probability of red. So this is going to be an experimental probability, right? We have some numbers and we're looking for the probability. So the probability of red is going to be our number of red shirts, or number of people wearing red, over our total number of people. Or that's going to be 6 over 20, or 3 over 10. So you have a 30% chance of it being somebody wearing red. All right, let's look at some more examples. Let's look at what's your chance, or what's your probability of rolling 5 on a die. So what's your probability of 5? This is a normal die. So that's going to be, what's the number of times where we have a 5? Our whole sample space, right? Our whole number of outcomes is 1, 2, 3, 4, 5, and 6. Our total number of winning ones where we get 5 is going to be that. So we have a 1 chance out of 6, right? We have a total of 6 different opportunities that we can pull this. Only one of them is a success. Okay, what's the probability, though, of rolling 2 dice that add to 5? 2 dice that add to 5. Now this gets a little more confusing because now we have 2 dice. So we could have the first die roll a 1, then we could roll 1, 2, 3, and so on, but that's going to become a pain to write out that way. So let's try to think about this a little bit. What's our sample space? What's the total number of outcomes? Well, we can roll 6 possibilities on the first die. We can roll 6 possibilities on the second die. This goes back to that fundamental counting principle, right? We have 6 chances, and we have 6 chances, meaning there's 36 different outcomes. Now, how many of those are going to add to 5? Well, if we roll a 1 and a 4 on the one die, that'll add to 5. If we roll a 2, then a 3, that'll add to 5. If we roll a 3 on the first and then a 2 on the second, that'll be 5. And if we roll a 4 on the first and a 1 on the second, that'll be a 5. Notice how these are repeated. This isn't the same thing. This is saying a 1 on the first die and a 4 on the second. This one is saying 4 on the first die, 1 on the second. But what this means is we have 4 different winning outcomes. So we have 4 winning outcomes, right? Our probability of 2 dice adding to 5 is going to be our number of winning outcomes. So 4 winning outcomes over our total number of outcomes. So 4 winning outcomes over 36 outcomes. That's going to be equal to 2 over 18, or 1 over 9. That's going to be our probability of that. All right, now let's look at some things that are a little bit more confusing. This gets covered more in the next lesson, but Gallagher covered it now, and because we're sticking to each other's course, I'm going to be working on this a little bit. Actually, I lied. One more. What's the probability of not rolling a 3? This is something we call a complement in the field of probability. So what's the probability of not rolling a 3? Well, there's 5 different opportunities where we can not roll a 3, and 6 total, right? If you roll a 1, 2, 4, 5, or 6, that's going to work. But if you roll a 3, it's not. All right, so now we're going to cover looking at some probabilities of some things combined. We're going to be doing this dealing with cards. So for those of you who don't know, cards, we have 52 cards, and those are split evenly into red cards and black cards. Inside the reds, you have 2 different suits. One of those is the heart. One of those is diamonds. And within black, you have 1 suit which is spades, and you have 1 suit which is clubs. Within each of these, you have 13 different cards. So in hearts, for example, you're going to have an ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, as well as a jack, queen, king. So that's the way this splits down. Each suit has an ace through king. You have 2 suits that are red, 2 suits that are black for a total of 52 cards. All right, so let's look at this. Let's say, what's the probability of pulling a red or an ace? Okay, so let's look at this. What's our total number of possible reds? Well, we have 52 divided by 2. We have 26 possible reds we can pull. And how many aces? Well, we have 1 for each suit, so we have 4 different aces that we can pull. But we have to look for overlap, right? Are all of those aces not red? No, we have 2 red aces, so we have 2 things that are counted twice. So we have our reds, then our aces, but 2 of our aces are red, so we have to remove those. Our probability is going to be 26 plus 4 minus 2 over our total number of cards. Or this is going to be 30 minus 2, 28 over 52. Then you go ahead and reduce that. So our rule, and once again we'll cover this a little bit, is you got to remove overlap. Overlap. All right, let's do another one of these. Let's say you're looking at the probability of pulling a club or a jack. So how many clubs do we have that we can pull? That's supposed to be our clubs, if I could draw this any better. So we know there's going to be 13 clubs that we can pull, right? 52 divided by 2 divided by 2. How many jacks can we pull? Well, there's 4 different jacks we can pull. But is there a jack of clubs? There is. So we counted one thing twice in there. We have to remove that. And this is going to be out of 52 cards. So this is going to become 17 minus 1, 16 over 52. And you'd go ahead and reduce that using math frac or turn that into a decimal. All right, now let's talk about one more. What's the probability of pulling a club and a jack? Notice this is slightly different, right? We're not talking about pulling a club or a jack. Now we're saying, what's the likelihood of us pulling a club that happens to be a jack? So how many clubs and jacks are there? There's just one. There's the jack of clubs, and that's our only chance out of that 52. So when you're dealing with looking at 2 things, one or the other, you're going to look at the probability of both, right? So you're going to look at how many you have of one, how many you have of another, and then you're going to remove the overlap. All right, one last set of examples. Let's say you are looking at 3 children. You're going somewhere and you know this person has 3 children. You don't know whether they're boys or girls. We're looking for the likelihood of there being 2 boys. Or the probability of there being 2 boys out of those 3. And now I know that there's the potential, or we can argue about there being different genders, any variability in there, but for right now, for the probability, we're going to keep this simple and say there's just girls or boys to try to figure this out. All right, so we have 3 children, and we're looking for when there could be 2 boys. So we have to figure out how many different groups we have that could have 2 boys. So let's say the first one, we have a boy. We could have a boy, boy, and a boy. We could have a boy, girl, boy. But you can see this is going to get a little bit confusing. Or this is going to get a little tedious. So let's make a table for this. So we're going to have the potential for the first one to be a boy or a girl. Then we have the potential for the second one to be a boy or a girl. And then the third one to be a boy or a girl. All right, so this is our sample space. This is all of our different potential options. Now we can write these out pretty simply. We have boy, 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 girl, boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, and girl, girl, girl. All right, how many of these do we have just 2 boys in? Well, we have 1, 2, 3, it looks like. Yep, just 3. So our probability of 2 boys is going to be, we have 3 where we have that, over how many do we have total? 1, 2, 3, 4, 5, 6, 7, 8. So there's a 3/8 chance, or a 3/8 probability, that we will have 2 boys. All right, that's it for this lesson. Let's give you guys some practice problems. I'm going to give you one of each of the different types, so make sure you are practicing these. Let's go with the first one. Let's say you're flipping a coin. You see that you have heads, heads, tails, heads, tails, tails, tails. 3, 4, 5, 6, 7. We'll make it 8. I want you to figure out what the probability is, the experimental probability is, of flipping a tails. Then I want you to look at a couple of experimental probabilities. I want you to look at the probability of pulling a spade or a club. Look at the probability of pulling a red and a 5. And look at the probability of a red or a jack. And then finally, you have a square, a 10 by 10 square. And the area you want to hit, let's say this is a dartboard, looks like that, and it's 5 inches by 6 inches. So go ahead, pause these, make sure that you're doing these, and then we'll come back to answer them. All right, so looking at this first one, we're looking at the probability of tails. The experimental probability is the number of times this showed up over the total number of times. So our probability of tails will be, how many times show up? 1, 2, 3, 4. So it's going to be 4 over, how many heads did we, or how many total did we have? 1, 2, 3, 4, 5, 6, 7, 8. So it's 4 over 8, or 1/2. That's our answer for the first one. All right, for number 2, we're looking for the probability of spade or club. So that's going to be equal to, we know there's 13 spades and there's 13 clubs. Now, are there any spades that are clubs or clubs that are spades? There are none, so we have no overlap. So the answer for this is the probability of a spades or a club will be the 13 spades plus the 13 clubs over your total of 52 cards, to make it 26 over 52, or 1/2. Right. What about the probability of a red and a 5? So the question is, how many red 5s are there? Well, you can have the 5 of diamonds and you can have the 5 of hearts. So you have 2 different red 5s you can pull from, right? And you have 52 cards total. So this becomes 1 over 26. Finally, what about a red or a jack? Probability of a red or jack. How many reds can you choose? That's going to be, you have 26 reds you can look at. There's 4 different jacks that you can pull, but 2 of those jacks are red, so we counted them twice. And that's over our total of 52. So that's going to be 28 over 52, which you're going to reduce using your math frac. And finally, for this one, we're looking for the geometric. So the geometric is this area divided by the big area. So this is going to be 1/2 of 6 times 5, or 3 times 5, 15 over 10 times 10, 100. So this is going to be 15%, or whatever that reduces down to. All right, go ahead and get started with the